Okay, let's talk about some properties of logarithms. I'm just going to do some of the properties, some of the simple ones. So recall that we had y equals a to the x was an exponential function. And you could always rewrite this as a log function. So this is exponential. And let's write this as a log function. I always start with the base a. So log sub a, log base a. You don't really say sub a, you say log base a. And then you take the y value and you stick it in here as the argument, and you switch it with the x value. Now this isn't an inverse. This is not an inverse. It's just rewriting the log function. The exponential function as a log function. You should be able to go both ways, back and forth. So we use this basic idea a lot when we're talking about log functions. So y equals log base a of 1 is something you should know. You should know the answer to that instantaneously. And with a little practice that should come. But the reason is because you should always be thinking what a log function looks like whenever you see this. And this sucker is going to always cross here at 1, 0. So log base 1 always equals 0. Conversely, you can rewrite that. So that's essentially saying that a raised to the power of 0 equals 1. That can make it easy for you to solve problems with logs by knowing that you can always write your logs in terms of an exponent. So that's how the two relate. Okay, thinking again about the ideas of switching back and forth. Log base a of a, so say a is the argument here, equals something, equals y. Well, think about it this way. If we wanted to, so we got base a raised to the power of y equals a, and that's rewriting it as an exponent. What has to happen for that to occur? Well, y needs to be equal to 1. So, log base a of the same argument a equals 1. And the natural log of e equals 1. Same thing. The natural log is log base e. And we could always rewrite this too. A raised to 1 equals a. So those are two pretty intuitive properties. Let's think about this now. Okay, there's a property of inverses that states a function whose argument is the inverse of that function. Well, the answer to that is just the argument of the inverse function. A lot of arguments there. So a function of whose argument is the inverse function is just the argument of that inverse function. So if this is an idea, I'm just going to state it. If this is an idea, then we know that y equals a to the x, and the inverse of that we have found to be y equals log base a to the x. These are inverses of each other, go back and forth. Notice I'm not rewriting this as a log. I'm actually writing the inverse of this, which is a whole different function. So then if I look at the function y equals a raised to the power of log base a of x, So this is essentially the argument is the inverse of my original function. The answer then is just x. Because this is just f of f inverse of x. So that's true. And likewise, for a similar reason, this is true. Y equals, say, the log base a of a raised to some power, say r. Well, this is just going to equal r for the same reason, because this is f of f minus 1 of x. A to the r power is the inverse of log base a to the something, or log base a to the r, I guess. So this equals r. This is one of your most important log properties to remember or to learn, because you're going to use that to simplify equations. So let's do some examples, since that's kind of important. Okay, here's like one of the most important examples you have. This is something you'll do all the time. If you take the natural log of e to the kt, you end up with just kt. It's a great way to simplify a relationship. Take the natural log of an exponential function, you just get whatever is in the exponent. If you have log base 10 of 10, notice the base is the same here, 10 to the raised to the power of 5x plus 2. Doesn't matter what's in the exponent. If the bases are the same, this just equals what's in the exponent, 5x plus 2. And then going the other direction, if you have 4 raised to the log base 4 to the 10x, so this is all in the exponent here, this just equals 10x. So super important property. This guy especially is this sort of relationship you're going to come into contact with a lot. Okay, let's talk about the product quotient rule of logs. Suppose you have log base a of m times n, so two values multiplied by each other in here that you could separate. Then this is just log base a of m plus log base a of n. Another way to simplify equations. And if you had log base a of m over n, then this equals log base a of m minus log base a of n. And quick example here, suppose you have log base a of 27. Well, it's the same thing as log base a of 3 times or plus log base a of 9. You could even go further here and say this is log base a of 3 plus log base a of 3. So this is plus log base a of 3. So this equals essentially 3 log base a's of 3. Because these were all the exact same functions. That's interesting. And that leads us to our next important relationship. Essentially what you're saying here is that log base a of 3 cubed equals 3 times log base a of 3. This is essentially what you're saying, right? And this is actually our, if I write this in a more general sense, this is we can look at this as log base A of some base raised to the power r equals r times log base A of some base. This is another very important, I'll put a star by it, another very important log property. Because you use this to simplify your relationships that you're working on. So for example, so you have log base 8 of 100. Well, this is the same as log base A of 10 squared equals 2 times log base A of 10. Sometimes you can completely get rid of the log function. So you have log base 10 of 100. Well, this is log base 10 squared equals 2 times log base 10 of 10. And what happens when you have the log and the base the same? Just equals what's in the exponential. So this is the same thing as 2 times 1, because it's 10 raised to the 1 power, equals 2. So this more complicated log function just simplifies to 2. Or say you have an equation with a log function at 0 equals natural log of 6 raised to the power of x squared minus 9. Well, this equals x squared minus 9 times the natural log of 6. This is in the exponent, I can pull it out in front of the log function. So natural log of 6 is like a constant. Say this equals 0. So now I can divide both sides by natural log of 6. Since this is a constant, you can take your calculator out and calculate this number. It is something like 1.792 or something. So if I divide both sides now by, let's do this in red, or let me just write it over here again, x squared minus 9 times natural log of 6. Now say I divide this by natural log of 6 and natural log of 6. We divide that out now, and we're left with just x minus 3, x plus 3. So your answer is x equals 3 and x equals minus 3. Because that's what makes these equal 0. One of these, if either of these, so this is like saying either this is x minus 3 equals 0, or this is x plus 3 equals 0, which leads to x equals 3 or x equals minus 3 as your answers. So it shows you how you can playing around with logs are like playing puzzles.